Okay, let's start today's lesson with a quick review. This is the graph of the function y equals x squared minus 2x minus 3. Now, on the graph, there are some important features that we learned about. They are the x-intercepts, sometimes called the zeros of the function, the y-intercept, and the vertex. And the vertex lies on this line that cuts it right in half and creates a mirror image of the graph, the axis or line of symmetry. So my first question is, which one of these points are we finding when you set the output y to 0 and solve for x for any quadratic function? If you said the zeros, you would be correct. The x-intercepts or the zeros of the function. All right, next. What do you find when you set the input x to 0 and solve for y? And if you said the y-intercept, you'd be correct. And finally, what can you determine when you find the vertex of the function? So if you find the vertex of the function, what are you determining? And that would be the maximum or minimum output of the function. So we've spent a lot of time learning how to find the zeros of the function or solving quadratic equations when they're set equal to 0. We know how to find a y-intercept, and we've spent a lot of time learning how to find the vertex. Now, why did we do all of this? Today, we're going to be using quadratic functions to solve real-world problems. Now, when we solve real-world problems using quadratic functions, what we need to do falls into 5 main categories. Finding the y-intercept or a starting point, finding the vertex for the purpose of finding a maximum or minimum value, finding the x-intercepts or the zeros of the function, and an output given an input or an input given an output. So let's take a look at our first problem and see what we need to do. The height of a football after it has been kicked can be modeled as a function of time using the following equation. H equals negative 16t squared plus 64t. And we want to know, how long did the ball stay up in the air? Now, if we want to know the answer to that question, how would we go about finding the answer? Would we find the zeros of the function, the y-intercept, the vertex, or would we find an output given an input or an input given an output? I'd like you to think about this and come up with an answer. Pause the video and see what you come up with. Pause the video now. All right, hopefully most of you said find the zeros. If you said find an input given an output, you'd also be correct, because when you find the zeros, that's exactly what you're trying to do. You set the output equal to 0, and you're trying to find the input that gives you that output. All right, finding the zeros is a special kind of category because we do it so often, and we're always setting the output to 0. So it's kind of its own thing. So go ahead and try to find the zeros of this function and see if you can answer the question, how long did the ball stay in the air? Go ahead and pause the video and we'll go over the answer when you're done. Pause the video now. All right, let's see how you did. So all of you could have solved this different ways. I set the equation equal to 0. Then I noticed a greatest common factor, so I factored out a negative 16t. And then I found the values of t that would make each factor 0. Negative 16 times what equals 0? Well, that would be 0. And then t minus 4, or what minus 4 would equal 0, and that would be 4. So the zeros are 0 and 4. So the place on this graph where the output is 0 is when s equals 0 and s equals 4. And that would make sense. So the ball is on the ground when it's kicked, and then it's also on the ground again when it falls back to the earth. So, and that took 4 seconds. So how long did the ball stay up in the air? That would be, the ball was in the air for 4 seconds. And we found that by finding the zeros of the function. So let's go to our next question. After how many seconds did the ball reach its maximum height? What was its maximum height? So there's two questions in there: the length of time it took to reach the maximum height and the actual maximum height. So hopefully this shouldn't be too hard. How would you go about finding the answer? I'm not even going to let you pause the video here because everybody should say, all together, the vertex. Very, very good. So go ahead and find the vertex. You have two options to find the vertex. You can convert to vertex form, or you can use our new little formula for finding the vertex, or the axis of symmetry, which allows you to find the vertex. However you accomplish it is fine with me. And go ahead and pause the video, and we'll go over the answer when you're done. Pause the video now. All right, let's see how you did. So I used the little formula because it's a whole lot faster, which is why we went through the trouble to derive the formula in the first place. So the axis of symmetry is x, or in this case the input value is t for time, equals 2. And so I plugged in 2 for the time, and I found the output h at t equals 2 is 64. So after 2 seconds, the height of the football, or the output of the function, is 64, so 64 feet. So the answer would be the ball reached a maximum height of 64 feet 2 seconds after it was kicked. All right, next question. How high was the ball 1.5 seconds after it was kicked? How high was the ball 1.5 seconds after it was kicked? So how would we go about finding this answer? Think about this for a moment, and let's see if you can come up with the right answer. So pause the video now. Okay, in this problem, we're given a value for t. How high was the ball 1.5 seconds after it was kicked? And the unknown value, or the value we're trying to look for, is the value of h. So it seems like we're being given an input t, and we're trying to find an output h. So we're trying to find the value of h, the height, when the value of t, the time, is 1.5. So this shouldn't be too difficult to figure out. Pause the video and see if you can find the value of h when the value of t is 1.5. Pause the video now. All right, now what you should have done is just plugged in 1.5 for t, simplified, and you would have seen that the value of h is 60. So after 1.5 seconds, the height of the football was 60 feet. And our next question. For how long was the ball above 40 feet in the air? For how long was the ball above 40 feet in the air? This one's a little bit trickier, so how would you go about finding this answer? I want you to think about this for a second and see if you can figure it out. So go ahead and pause the video now. All right, so the answer is you're trying to find the time, or in this case the times, when the ball's height is at 40 feet. So in this case, we're being given an output, and we're trying to find an input that gives us that output. So when the height is 40 feet, what are the values of t? Now, we say the values because if you think about it, if the maximum height is 64 feet, then when is the ball going to be 40 feet high? Well, it's going to be 40 feet somewhere on the way up, and it's going to be 40 feet again somewhere on the way down. And we want to know how long did it take, or for how long was the ball above 40 feet. So we're trying to look for the interval between those two times. So I'm going to go ahead and let you pause the video and see if you can work it out for yourself, and then we'll go over the answer. So pause the video now. All right, so the first thing we need to do is we need to set the output equal to 40, because we know the height is 40 and we want to know the value of t, or the values of t, when the height is 40. So here's our equation. We want to solve this equation. So the first thing we need to do is set it into standard form by setting one side equal to 0. So we've got the equation negative 16t plus 64t minus 40. Now, you could go ahead and plug these values into the quadratic equation and solve for t. Nothing is stopping you from doing that. But to make your life easier, if you've noticed, what I've done is I noticed that there was a common factor of negative 8. So I just factored that out, and then I divided both sides by negative 8, leaving me with the quadratic function 2t squared minus 8t plus 5. Now, I can use these values in the quadratic function, the quadratic equation, I can use these values in the quadratic formula and it'll still work. Now, you're probably wondering why. Why can we use these smaller values instead of these larger values? And the answer is simple. This greatest common factor, negative 8, that factor is not responsible for getting us to a product of 0. This trinomial is responsible for getting us to a product of 0. So if we found the value of t that made this expression equal to 0, well, that would make the whole expression equal to 0. And that's why that works. So we're going to plug in 2, negative 8, and 5 for our a, b, and c into the quadratic formula. Simplify. There's our precise answer, but we need actual usable values. So we use decimal equivalents. And we know that the football was at a height of 40 feet at approximately 0.78 seconds and 3.22 seconds. So we want to know, when was the football above 40 feet? So we're looking for the interval between that. So if you got this far, that's great, but that's not how to answer the question. All right, the answer to the question is the time between these 2 points. So and the time between those 2 points was approximately 2.44 seconds. So the ball was higher than 40 feet for approximately 2.44 seconds. And that's more than half of the total time the ball was in the air. All right, let's take a look at a different type of problem. Dante catapulted a water balloon into the air from the roof of his house. Its height h in meters after t seconds can be modeled by the function h equals negative 4.9t squared plus 20t plus 5. Now, before we start answering some questions about this situation, I want you to examine this graph and tell me how it differs from the last one we saw. So take a moment, analyze it, and come back after we pause the video. Pause the video now. All right, so hopefully you noticed that this graph does not pass through the origin, and therefore the y-intercept is not one of the zeros. And we know our y-intercept is often our starting point. Also, there is a positive and a negative 0. So one of the zeros is over here on the negative side of the horizontal axis, and over here there's a positive 0. So why is this important? Well, if you think about it, negative values for t, or time, don't really make sense in this context. All right, Dante catapulted a water balloon into the air from the roof of his house. Its height, h in meters, after t seconds can be modeled by the following function. After t seconds. So basically, this model only means something after Dante has catapulted the water balloon. How can you have negative time in that context? Time only matters going forward from that moment. We can't kind of recreate what happened before because nothing happened before. The water balloon was just sitting there in the catapult. It wasn't moving. So these values over here, right, we're going to pretend they don't exist because they don't make sense in the context of the problem. Right? These outputs, right, because they don't make sense, these inputs, I should say, are not in the domain of this function. Although mathematically they exist, right, they don't exist in the real world. Mathematics can be used to model the real world, but it's not the same as the real world. So sometimes we have to limit our domain, all right, to make sense of a problem. The other thing you might have noticed is the inputs continue to move downward as time moves forward. Well, this is one of the zeros, so this is probably where the balloon hit the ground. Now I'm going to let you in on a little secret. When a balloon hits the ground, it stops. It does not continue to move through the ground. All right, so all of these outputs here are also meaningless. All right, although mathematically they exist, they make no sense in the context of the problem. So we're also going to pretend that those don't exist. And so this is a better representation of a graph, all right, or of this model if we limit the domain. Now, when you look at a graph of a function, the graph is not always going to represent this limited domain. So it's important to interpret the graph in the context of the problem. All right, but now that we're ignoring these other values, we can answer this other question: how high is Dante's roof? Now think about that for a moment, and let's see if you can figure it out. All right, pause the video, and we'll go over the answer in just a moment. Pause the video now. All right, so nothing is said about Dante's roof other than the fact that he catapulted a water balloon into the air from the roof. So how are we going to figure out how high Dante's roof is? Well, the water balloon is on Dante's roof the moment it is catapulted. And the moment it's catapulted, all right, no time had gone by. So we want to know the height of the balloon at t equals 0. And we know that if we set t equal to 0 here and t equal to 0 here, then the output is going to be this constant, or our y-intercept. And we can see that right here on the graph. All right, looks like Dante's balloon started to move up right about here. And what do we call that point? The y-intercept. So if we find the y-intercept, we find where the balloon was when it was catapulted, and we can find the height of Dante's roof. So the height of the balloon at the moment it was catapulted would also be the height of Dante's roof. The balloon had a height of 5 meters at t equals 0, and therefore Dante's roof is 5 meters high. If you got that, congratulations. All right, let's go to the next question. When will the balloon hit the ground? Now, we've already gone over the different possibilities of what you could do, so I'm going to let you take it from here. Pause the video. We'll go over the answer when you're done. Pause the video now. All right, so when will the balloon hit the ground? Well, what is the height of the balloon when it hits the ground? The height is 0, so we're trying to find the zeros of the function. So we set the output equal to 0, and we solve the function. Guess what? This is not a function you should try to factor. So we're not solving by factoring. T is in 2 places, so we're not solving by square roots, which leaves us the quadratic formula, our favorite. All right, and so when we solve the quadratic formula, we get 2 answers. T equals negative 0.24 and 4.32. Now, we've already discussed how this point simply doesn't make sense in the problem. So although the answer, or I should say the solution to this equation, all right, has 2 values, one of these values is completely irrelevant. It's garbage. So we ignore it, pretend it doesn't exist, and we interpret the positive value as the answer to our question. The balloon will hit the ground after approximately 4.32 seconds. All right, next question. What is the maximum height of the balloon? I'm not even going to let you pause the video, all right, in order to answer the question, what do you need to find in order to answer this question? We all know if it's a maximum, we're trying to find the what? The vertex. Very good. But I will let you pause to find the vertex and to find the answer to the question. So pause the video now. All right, let's see how you did. So again, I'm using our nifty little formula that we've derived. All right, so the axis of symmetry is somewhere around 2.04. All right, I plugged that into the function, and I got approximately 25.41. Now, you should concentrate on the process here and not the exact answers. If you rounded slightly differently than I did and you got a slightly different answer, that's fine. But if your process is the same, that's really what I care about at this point. So the balloon reaches a maximum height of approximately 25.41 meters. And our next question, how high is the balloon after 1 second? So pause the video and see if you can figure that out. Pause the video now. Okay, so this question gives us a value for time and asks us about height. So it should be pretty simple. We're being asked to find an output given an input. So we input 1 and we get out 20.1. So after 1 second, the balloon is 20.1 meters above the ground. And our last question, for how long is the balloon more than 20 meters high? Pause the video and find the answer now. All right, let's see how you did. So this is a question about time. For how long is the balloon? And this is a question about time, and we're given a height. So we're trying to find an input given an output. So we set h equal to 20, and we solve that equation. All right, so we're going to subtract 20 from both sides, putting the equation in standard form, identify our a, b, and c, plug it into the quadratic formula. All right, and now we know that the balloon was at a height of 20 meters, approximately 0.99 seconds after it was catapulted, and approximately 3.09 seconds after it was catapulted. And so if it was 20 meters on the way up, all right, it started being above 20 meters at 0.99 seconds, and it fell below 20 meters at 3.09 seconds. So what was the time interval between those 2 points? Approximately 2.1 seconds. All right. Hopefully you did a really good job on all those and you've prepared to tackle this question on your own. All right. The height of a flare fired from the deck of a ship in distress can be modeled by the following function. H equals negative 16t squared plus 104t plus 56, where h is the height of the flare above the water in feet and t is the time in seconds. I would like you to find the following: the time it takes for the flare to hit the water, the maximum height of the flare, the initial height of the flare. I want you to find the height of the flare 4.7 seconds after it was fired. Round your answer to the nearest tenth. And how long did it take for the flare to reach a height of 150 feet? So these are 5 questions. I want you to work on all 5 of them, and then when you're done, we'll go over the answers. So go ahead and pause the video now. All right, let's see how you did. Let's tackle these one by one. All right, so the first one, find the time it takes for the flare to hit the water. Well, when the flare hits the water, the height would be 0, so we're trying to find the zeros of the function. We set the output equal to 0, and we try and solve. Now, you can solve using any method you want. If you use the quadratic formula, good for you. I'm going to try solving by factoring, and that's what I did here. So I factored out a negative 8. I looked at the trinomial that resulted, and I quickly was able to factor it into 2t plus 1 times t minus 7. Using the zero product property, I was able to determine the zeros are t equals negative 1/2 or t equals 7. Now, we know that this function only models the height of the flare after it was fired. So a negative value for time wouldn't really make sense in this context, so we can go ahead and ignore this value. So that leaves us with t equals 7, which means it took 7 seconds for the flare to hit the water. For the maximum height of the flare, all we have to do is find the vertex. Now we know we can calculate the axis of symmetry. All right, so the maximum height of the flare was achieved 3.25 seconds after it was fired, and the height at that point was 225 meters. The initial height of the flare was the height of the flare at the moment it was fired, or when t equaled 0. So here we're just trying to find the y-intercept. So, I'm going through the math here, but by now you should know the constant of a quadratic function is always going to be its y-intercept. So it's 56 meters. Number 4, find the height of the flare 4.7 seconds after it was fired. This asks you to find the height, or the value of h, given a time, or the value of t. So all we have to do is set t equal to 4.7 and find h, which just requires us to simplify this expression, and that gives us 191.36 meters. I'm sorry, feet. I think I said meters before. Ignore me. It's feet. Okay, and finally, number 5. All right, how long did it take for the flare to reach a height of 150 feet? Well, this asks us to find the time given a height. All right, so we set the height equal to 150 and we solve for t. So we first set the equation equal to 0 on one side, and now we can either solve by factoring if it's factorable, or using the quadratic formula. So I chose to use the quadratic formula here, and when I do that, I get approximately 1.1 seconds.